Have you ever thought about how reality works at the smallest scale beyond what our eyes can see? Welcome to the world of quantum physics. This fascinating branch of physics takes us into a realm that, quite literally, defies common sense. It deals with the behavior of matter and energy at the smallest scales, such as the scale of atoms and subatomic particles. Think about it as the rule book for the basic building blocks of the universe. It's here where particles can exist in multiple states at once, where they can be both particles and waves, and where the act of observing can change the outcome. It's a world where the traditional laws of physics are turned on their head, and where the impossible becomes possible. As we delve deeper into this world, we'll explore how these mind-bending concepts challenge our understanding of reality and the universe. So, buckle up. Let's dive into the fascinating world of quantum physics. Imagine if you could be in two places at once. Sounds impossible, right? Not in the quantum world. Welcome to the realm of quantum superposition, a principle that allows quantum systems to exist in multiple states simultaneously. Think about flipping a coin. While it's in the air, you can't tell if it's heads or tails. It's in a superposition of both states. The same goes for a quantum particle. It can exist in a superposition of being both a particle and a wave, until it is observed or measured. The act of observation collapses the superposition into a single state, much like catching the coin reveals whether it's heads or tails. But here's where things get even more fascinating. In the quantum world, particles such as electrons and photons don't just behave like particles, they also behave like waves. This is known as the wave-particle duality. The wave-like nature of particles allows them to exhibit interference and diffraction patterns, similar to the ripples you see when you drop a stone into a pond. On the other hand, their particle-like nature allows them to possess discrete energy levels, just like a staircase with specific steps. Imagine a beach ball bouncing along the seashore. It has a specific location and moves in a defined direction like a particle. But also picture the ocean waves undulating and spreading out, not confined to a single location. That's the wave aspect. Particles in the quantum world are like that beach ball riding those waves, exhibiting both characteristics. So, how do we reconcile these two seemingly contradictory behaviors? Well, that's the beauty and mystery of quantum physics. It's like a chameleon, changing its appearance based on how we choose to observe it. This dual nature of particles is truly one of the most intriguing aspects of quantum physics. It shatters our conventional understanding of reality and opens up a universe of possibilities that are as limitless as they are fascinating. It's a reminder that at the deepest levels, the universe is not just stranger than we imagine, it's stranger than we can imagine. How well can you know a quantum particle? Not as well as you might think. First, let's talk about Heisenberg's uncertainty principle. This principle, formulated by Werner Heisenberg, is an integral part of the quantum world. It tells us that we cannot know both the position and momentum of a particle with absolute precision. The more we try to pin down one attribute, the blurrier the other becomes. It's like trying to catch a hummingbird in flight. The faster it flutters, the harder it is to pinpoint its exact location. This isn't due to any limitation in our measurement tools, but rather, it's a fundamental aspect of quantum particles themselves. They simply do not have precise values of both position and momentum at the same time. Now let's switch gears to quantum entanglement. This is a phenomenon that seems to defy common sense and yet is fundamental to quantum physics. Imagine we have two particles that are entangled. These particles, no matter how far apart they are, will have their states intertwined. If we measure one particle, we instantly know the state of the other, regardless of the distance between them. It's as if two friends were separated, one sent to Mars and the other left on Earth. Yet the moment the friend on Mars decides to stand up, the friend on Earth instantaneously knows to sit down. These concepts, the uncertainty principle and quantum entanglement, might seem strange and counterintuitive. They challenge our everyday understanding of how the world works. But in the realm of quantum physics, they're the norm. They shape the behavior of particles and ultimately the structure of the universe itself. In essence, the quantum world is a place of beautiful chaos, where particles can be entwined over vast distances and where certainty gives way to probability. It's a world that's still being explored, with mysteries yet to be unveiled and understood. Quantum entanglement and the uncertainty principle, two seemingly strange phenomena, are at the heart of quantum mechanics. Ever wished you could walk through walls? Quantum particles can. This is not a figment of science fiction, but a quantum mechanical phenomenon known as quantum tunneling. Picture this. In the classical world, if you throw a ball at a wall, it bounces back. The wall, a barrier, is impassable. But in the quantum world, particles like electrons don't always behave as expected. They can actually pass through barriers that would be insurmountable according to classical physics. Why does this happen? Well, remember when we talked about wave-particle duality? That's where this comes into play. Particles can exhibit wave-like properties, and these waves can extend through barriers, even when the particle doesn't have enough energy to overcome the barrier classically. This means that there is a probability, albeit often very small, that a quantum particle will be found on the other side of a barrier. This is quantum tunneling. It's not just an interesting quirk of the quantum world. Quantum tunneling has real-world applications, for example, in tunnel diodes used in high-speed electronics. And it's a key process in nuclear fusion, the reaction that powers our sun. Now let's shift gears and talk about quantum computing. It's a field that leverages the principles of quantum mechanics to perform computations. Unlike classical computers, which use bits that can be either 0 or 1, quantum computers use quantum bits or qubits. These qubits, thanks to the principle of superposition, can exist in a state that is a combination of 0 and 1 at the same time. This gives quantum computers a potential computational power far beyond that of classical computers. They could, in theory, solve complex problems much faster, from factoring large numbers, which has implications for cryptography, to simulating complex chemical reactions, which could revolutionize drug discovery. However, building a practical quantum computer is a huge technological challenge. But researchers worldwide are working on it, and we've already seen promising advancements. Quantum tunneling and quantum computing, two applications of quantum mechanics that show the potential of this field. Quantum physics, a field that challenges our intuition and opens up a whole new world of possibilities. So, let's take a moment to reflect on the journey we've embarked on today. We've delved into the captivating realm of quantum physics, a science that deals with the behavior of matter and energy at the smallest scales, such as the scale of atoms and subatomic particles. This is the world where the ordinary rules of physics that we're accustomed to no longer apply, and new fascinating principles take their place. We discussed the concept of quantum superposition, a principle that allows a quantum system to exist in multiple states simultaneously. It's a mind-boggling idea that an electron can exist both as a particle and a wave until we decide to take a closer look. This is not just a theoretical concept, but a reality in the quantum world. We then moved on to wave-particle duality, another cornerstone of quantum physics. This principle tells us that particles such as electrons and photons can exhibit both wave-like and particle-like properties depending on how we choose to observe them. It's as if these particles have dual identities, and they reveal one or the other based on our interaction with them. Then, there's the uncertainty principle, a fundamental concept formulated by Werner Heisenberg. This principle states that it's impossible to know both the position and momentum of a particle with complete accuracy. The more precisely we try to pin down one quantity, the more elusive the other becomes. This principle reminds us of the inherent limits of our ability to measure and predict in the quantum realm. We also explored the fascinating phenomenon of quantum entanglement. This is a situation where two or more particles become so intertwined that their individual states can't be described independently. The most mind-bending part is that changes in the state of one particle can instantly affect the state of the other, no matter how far apart they are. This concept, while counterintuitive, has been confirmed experimentally and holds great promise for quantum communication and information. Quantum tunneling was another intriguing principle we discussed. This is a quantum phenomenon where particles can defy classical logic and pass through energy barriers that should have been impassable. This startling effect is due to the wave-like nature of particles and their ability to exist in regions where classical physics says they shouldn't. Finally, we touched upon the exciting field of quantum computing, an application of quantum physics that could revolutionize the way we process information. Unlike classical computers that use bits for data processing, quantum computers use quantum bits or qubits, which can exist in superpositions of states. This quantum advantage has the potential to solve complex problems much faster than classical computers. In conclusion, quantum physics is not just a branch of science, it's a key to understanding the fundamental building blocks of the universe and how these particles interact with each other. It's a doorway to new technologies, new materials, and new ways of encoding and protecting information. As we continue to delve into the quantum world, who knows what other fascinating insights await us? Stay curious, and keep exploring the quantum universe.